Welcome dear students. Today we learn the analysis of a beam by a flexibility matrix method. Now suppose this is a beam, is one end fixed and here is a one is a overhang. So the beam A, B, C, D, this point load acting at 2 meter from this support is 100 kN and wheel is 15 kN per meter. This on the span BC and on the span CD also. Now in case of this flexibility matrix, the first step is to calculate the DI, degree of interluminancy. Now if you neglect the horizontal reactions and horizontal the equilibrium conditions, so here DI is equal to what? The unknown force, that is R minus this 2, because we are not considering the sigma fx. So we are also neglecting the horizontal reactions. So here is 2, 3 and 4. So R 4 and equation available is 2. So here DI is equal to 2 for this beam. Now 2 means we have to release the 2 forces from these 4 unknowns. So now the first choice is what? Is remove the RB reaction and RC reaction. So this structure is called as a release structure. Release structure. So this is one choice, is to remove the reaction RB and remove the reaction RC. And for this, then we have to use the Untitled method or various methods, that is to find the DQL at B and DQL at C. So that methods are tedious. So another choice is to remove the bend moment from this B support and from support A. Means we have to insert the hinge at A and insert the hinge at the B. This is the simplest one method for the analysis of the beam by flexibility matrix method, is to release the moment. So we have released this moment, so we are taking this as a consideration. So now for the simplification, we modify this beam like this here. So if you insert the hinge here, so there is no connection between this beam AB and BC. So like this beam is AB separately and this beam is BC separately. Now here this overhang we can convert into the support moment, 15 into 2 into 1, so that is 30 kN meter. So now apply the rotation where we release the moment. If you release the moment, then apply the rotation. So we have released the moment at A, so apply rotation at 1. Then release the moment at B, so apply the rotation at 2. So here we got because of this 2, we got this 2 by 2 matrix. And these 2 are our unknowns. Just release are the MA and MB, so 2 are the unknowns. So now we develop the 1 by 1 matrix here. Now we know that this formula is DQ is equal to DQL, DQ matrix, then DQL matrix into F matrix into a Q matrix. So here what? Q matrix is the unknown force, means that forces that we release. So in our case, we have released the moment at A and moment at B. This is our coordinate 1 and this is 2. 1, 2. So write here the MA and MB. Then next is the DQ matrix. So that is what? Initial displacement at the coordinate, means at 1 and 2. So there is no any type of the initial displacement at coordinate 1 and at 2. So that is why this value is 0 and 0. So we got this Q matrix and DQ matrix. Now our aim is to develop the DQL matrix. That is the displacement cause at coordinate 1 and at coordinate 2 due to this external loading. Due to this external loading, so we got here the dql1 and dql2. Then next is the F matrix, that is the flexibility matrix. It means you have to apply the rotation at here and find out the flexibility matrix at 1 and at 2, then apply rotation at 2, then find the flexibility matrix at 2 and at 1. So now we develop first the flexibility matrix. So here at coordinate 1 is our coordinate 1. So we have decided this is our direction of coordinate 1. So this is the F matrix. This coordinate is 1, so 1 and 2. Now we are applying the unit rotation at the 1. So here 1 and here 1. So now due to this unit rotation, this will deflect like this. Okay. Now due to this rotation, here rotation is developed in the at the point 2. So our F11, that is equal to, due to this unit rotation, the flexibility is the L of this AB divided by 6EI. So L is equal to is 6E. Here in this case for this beam I is equal to 2I. So take here the 2I. So this becomes now, no, this is not this is 3. At here we are rotation applying here and development here. So this is not a 6, this is a 3. So this becomes the 1 by 3 into 2, 6 gets the cancel out. This is the EI. Now F21, that is the rotation developed at 2 due to the application of unit rotation at 1. So here rotation is transfer at here is a half. So that L AB again divided by the 6EI. So here developed rotation at 2 is a half. So L by 3I here, it is L by 6EI. Now the development direction is like this in anti-clockwise fashion, and we have assumed direction in this beam is the same. That is why this value is the positive, and that L is a 6 and 6 into E into 2I. So this becomes 1 by 2EI. So this is the development of the flexibility matrix. So apply the unit force at 1, unit rotation at 1. So that develop here the L by 3I, and then this will produce at the coordinate 2, that is L by 6CI. Then next, now here apply this rotation 2. So this will produce like this. Okay. So this is what? This is F. This is the F. Okay. This is coordinate 1. This is coordinate 1. Coordinate 2. Now we are applying the rotation at 2. So 2 right here and 2 right here. So now first we develop the F22. This is what? In this span also, and in this span is AB, and this span is BC. So here we are applying the rotation at here at 2 2. So that is LAB divided by 3EI for the beam AB, and plus for this beam is LBC divided by 3EI. So what is here? L is equal to 6. Okay. Now 3E, here I is equal to 2I. Then plus either L is equal to, here is a, for BC is a 4 and is a 3EI. So this becomes, this cancel out 1. So this becomes the 7 by 3EI. Now development of the matrix or development of the rotation at 1 due to the application of the rotation at 2. So that is F12 and that is equal to the F21 and that is the 1 by 2EI. So now here we have developed the flexibility matrix. F is equal to is 1, then 0.5, 0.5 and here is a 7 by 3 into 1 upon EI. So as per our formula, we got Q matrix, DQ matrix, we got the F matrix and remaining is the DQL matrix. So now DQL matrix here. This is load 100, then this is UDL 15 kN per meter and here is one moment 13 kN. This is 2 meter and 4 meter. Now here due to this load here deflection is like this. Due to this load deflection is like this. So this load produces the, in this way is our DQL1. So this load does not produces any effect at the coordinate 1. So DQL1 that is equal to the rotation or slope developed at this end way due to this only the load. So that formula is W into B divided by 6EIL into L square minus B square. So W is 100 into 4 divided by 6E into I is equal to 2I into L is equal to 6 into 6 square minus 4 square. So this value becomes a 111.11 divided by the EI. Now this is the DQL1. Now develop the DQL2. So here, now here this is UDL and this is a moment external. This is 15. Here is the load 100. This is 2, 4 and this is 4. So now our aim is to produce the DQL2. That is the rotation caused at the 2 due to this external loading. So at 2 this will produce a rotation in this direction, that is why it is positive, and due to this load here also produce the in this direction. So what we have assumed direction of this 2 and what the produces here is the same, that is why the rotation produced due to this load and this load both are the positive. So due to this load is what? Formula is W A divided by 6EIL into L square minus A square. Then plus due to this load is W L cube divided by 24 EI. Now this force or this rotation also produces the rotation at this dql2. Now here what, if you consider here any simply supported, if you apply here any moment m, so this will try to deflect the shape like this, and this moment or produces the rotation at 1 is ml by 3ei, and at this 2 produces the ml by 6ei. Now here the rotation produces in this direction like, and what we have assumed direction is the in this direction. So this is the opposite to each other, that is why take this minus, and this will produce the rotation at this 2 is the ml by 6ei. So now we are putting this value into this equation. So what is happening here? So 100 into 2 divided by 6e, I is equal to 2i into L into L square minus A square, then plus W, then L cube divided by 24e, here I is equal to I, then minus here ml by 6 m is equal to is 30 into 4 divided by the 6ei. So if you do the calculation, the final answer is the 108.88 divided by ei. So we got here this dql matrix that is equal to, what is here our 1, dql1 is how much, is 111.11, and this is 108.88 upon ei. So now we got all this matrix dq, dql, f and the q matrix. Now put all these matrix into our equation. That is here dq, that is, or right here dq is equal to dql plus f into q. So dq we know is 0 0, dql that is 111.11 and 108.88 into 1 upon ei, plus here flexibility matrix that is 1, 0.5, 0.5 and 7 by 3, here is 1 upon ei, then into this is q is ma and mb. So if you solve this equation, we got ma and mb, that is equal to directly minus 98.31 and minus 25.59. Now this minus, what indicate that minus? That we have assumed this will produce in this direction rotation or movement, but minus means we have to apply the fixed moments like in the opposite direction. Here also we assume the sagging, but this is minus means we have to apply the hogging bending moment. So final diagram of this bending moment is here. Draw first the free bending moment diagram. WAB by L, that is 133.33, and here is W L square by 8, that is the 30. Now here we have to apply the in opposite direction, so that produces the hogging bend moment, that is the 98.31, and at here is minus again hogging bend moment, so 25, and at here we know this is the 0 and this is the 30. So join this and join this. This is 25.59. This is minus, plus, minus, plus, and minus. So this is the final beam. Thank you.